Welcome to our fourth lecture of Chapter 10. Today we are going to learn how to draw some of these flower diagrams that show the overlap of the orbitals. How are we looking at the bonding between the hybrid orbitals in these molecules? And so previously we've talked about, when atoms or have like sp3 hybridization or sp2 hybridization when they are in molecules. And so we're going to learn how to show that through pictures. We're going to learn how to show the sigma bonds that overlap, and then the pi bonds, above and below the plane, as well as in front and behind the plane, if we need to, for those triple bonds. That's a little bit tricky to show in pictures, but that is the plan for today. So, a couple things. Hybridization was introduced to explain the molecular structure when valence bond theory failed to correctly predict them. So this is kind of like what we were talking about in methane, right? When we looked and we saw that carbon, its valence electrons, it had 2s and then 2p. Carbon has 4 valence electrons, so 2 of them would be in the 2s, and then 2 of them would be in the 2p. And looking at this, we would see that carbon really only has 2 electrons available for bonding, and so carbon should only make 2 bonds. But even if we, promoted one of the 2s electrons up to the 2p, and then it looked like this, 1 electron, and then, so if we promoted one of those electrons to the 2p, it still wouldn't have 4 identical bonds. It would have 1 bond that looks differently because it's coming from the 2s instead of the 2p. So again, last time we talked about the fact that then carbon actually hybridizes all of those orbitals, and instead of having 2s and 2p, it makes 4 sp3 hybrid orbitals that are all going to be identical, and it puts 1 electron in each of those, and now it can make 4 identical bonds. So this is the whole thing about hybridization, right? So instead of having the 2s and the 2p, we have sp3. So then the second bullet point, according to valence shell electron pair repulsion theory, electron pairs repel each other, and the bonds and the lone pairs around the central atom, they are generally separated by the largest possible angles. So we see some, that are 180 or 120 or, 109.5. Those are kind of our typical bond angles. Sometimes we'll see things like 90 in some of the bigger molecules when things expand their octets. And so then we're going to use these, flower diagrams. It's kind of what we call them. They kind of look like flowers. And they're used to show the overlap between the hybrid orbitals of the bonding atoms. And so this is usually like the central atom that we're going to be showing these hybrid orbitals for. So we're going to do lots of practice so you can kind of see how this goes. So this is methane. So if we look at this, sorry, I don't know what's happening with the font. That says valence orbitals for carbon before hybridization. So best of luck reading that. But if we look, before hybridization, like I was saying before, the 2s electrons and the 2p electrons, right? And so we've only got these 2 electrons available for bonding, and so carbon should only make 2 bonds, which we know doesn't happen. What we know happens is that carbon makes 4 bonds. So this one says valence orbitals for carbon after hybridization. Sorry about the font. But carbon takes these 4 instead of, right? So there's still 4 orbitals. So instead of having 1 2s and 3 2p, it makes 4 sp3 hybrid orbitals. It took 1 s and 3p orbitals and hybridized them and put 1 electron in each. So now we have 4 hybrid orbitals. And so the way that we're going to show this, so we know that the Lewis dot structure for methane look like this. Carbon in the middle, and it makes 1 bond to each of those 4 hydrogens. And so the way that we're going to draw this for the flower diagrams is we put carbon in the middle, and we are going to draw our hybrid orbitals. So if you recall, the way that we showed the sp3, right? So S is a circle, and P is a dumbbell, and the way that we show sp3 is we have this big lobe and then like a little lobe. I'm going to draw it just showing the big lobe because a bunch of the little lobes overlapping would be kind of confusing. So assume that the little lobe is essentially where carbon is, and I'm just going to show the larger ones. So like here, that is one lobe, right? And so like I said, the little one would go here, but I'm not going to draw all of them. One of our sp3 hybrid orbitals, and here's another, and here's another, and here's another. So there's the 4 sp3 hybrid orbitals, okay? So I usually will go through and write in them sp3, 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 right? So that I remember that those are sp3 hybrid orbitals. And then we'll show the hydrogen. So remember, hydrogen, right? Hydrogen just has one electron in its 1s orbital. So we're going to draw that as a circle because that's, you know, that's what hydrogen is. So, and we're going to show some overlap. Actually, show a little bit more in the future because I usually put those electrons in there too. So that's our hydrogen. I'll do it better on this one. Here we go. Hydrogen and the 2 electrons in the bond. We've got hydrogen and hydrogen. Okay, so that would be how we would show our flower diagram for our methane. So we show our 4 sp3 hybrid orbitals for carbon, and then each of our 1s orbitals for hydrogen, and we're going to show the overlap and the 2 electrons that are, you know, in that overlap forming that bond. Let's try another one. Okay, this is aluminum hydride. This is just the font. This is AL, not capital L, H3. And so before, oh man, fonts got crazy. Okay, I'm just going to rewrite all of this. So before hybridization for aluminum, we have 2 electrons in the 3s and 1 electron in the 3p. And then if we're looking at the valence orbitals for aluminum after hybridization, then we are going to have, right, we're going to hybridize these, you know, 1 of the 3s orbitals and 2 of the 3p orbitals so that we can have 3 electrons that are identical. Because if we think about aluminum hydride, it's going to be aluminum making 3 bonds to hydrogen. Okay, so the way it's going to turn out is that we have 3 sp2 hybrid orbitals and 1 3p orbital that we are just kind of leaving alone, that is not hybridized. We're just going to kind of ignore it. And so we're going to put 1 electron in each of these because we know aluminum has 3 valence electrons. So then when we're drawing this, we put aluminum in the middle, and we're going to draw its 3 hybrid orbitals here. Okay, and so this is, again, I usually write these sp2 just so I can keep track of it. And then it's going to make 3 bonds to hydrogen, and each one of those hydrogens just has that 1s, which we're going to draw as a circle, right? And so here we go, there's hydrogen, and it's 2 electrons, hydrogen, and the 2 electrons in the bond, hydrogen, and the 2 electrons in the bond. So that would be how we would draw it for aluminum hydride. Here's another one. Again, the crazy things here. This is ETHYNE, and the ENE is telling us that there is a double bond. So if we drew the Lewis structure for C2H4, we would come up with this. Okay, and so the valence orbitals for carbon before hybridization, it has 2 electrons in the 2s, again, 2 electrons in the 2p. After hybridization, so if we look at the Lewis structure, right, there are 3 areas of electron density. So we know that both of these carbons are going to be sp2 because there are 3 areas of electron density, the double bond and then 2, single bonds to the hydrogens. So the way that this is going to look after hybridization is it's going to have 3 sp2 orbitals with 1 electron in each. And then it's going to have a 2p orbital with 1 electron. Okay, so this is how, double bonds will always have 1 electron in that, 2p or 3p, because that's how we're going to form the pi bond. We're going to form the pi bond out of that 2p. And it looks like I didn't delete this, which I wanted to, but I'm going to draw it over here. So what we're going to do is we put carbon right? We have our 2 carbons. And in those carbons, each one will have a sigma bond that's being formed from the sp2 hybrid orbitals. So it has 3 hybrid orbitals, right? It's going to have, here's 1, here's 2, and here I'm going to make it kind of small, 3. So those are my sp2 hybrid orbitals. And then this carbon is going to have 1, 2, 3. Okay, those are all of our sp2 hybrid orbitals. And they are going to form our sigma bonds, direct overlap right here. So there's 1, and then these are going to the hydrogens. All right, so those take care of our 3 sp2 hybrid orbitals. And now we're just left with this 2p, and the 2p is what's going to form the pi bond. We know that in a double bond, we have a sigma bond and we have a pi bond. In single bonds, we just had sigma bonds, which we're showing with the overlap, but in that double bond, we have a sigma bond and a pi bond. So we've shown the sigma bond here, but now we need to show the pi bond. So if you'll recall, p orbitals are dumbbells, right, like that. So the way that we're going to show this in the flower diagram, like for this left carbon, I'm going to put a lobe above and below. And same thing here, above and below. So that's the p orbital for each of those carbons. And so now the way that we are going to show the overlap is we're going to just kind of, usually I'll, shade these of some kind so they look different from the sp2 or sp3 hybrid orbitals. I usually just kind of fill them in so that they look different. So those are the p orbitals. So above and below will be how we show this pi bond. Okay, so we have sigma bonds from the overlap going to all of the hydrogens. Then we have a sigma bond for the overlap in the middle here between the carbons, and then we have a pi bond above and below the plane for those carbons. Okay, let's try another one. ETHYNE. So we have, again, the valence orbitals for carbon before hybridization, and then after, the Lewis structure first. And so if we drew C2H2, there would be a triple bond, and then a single bond going to each of the hydrogens. So since those carbons have 2 areas of electron density, we know that they are both sp hybridized. Okay, so after hybridization, we're going to have 2 sp orbitals and 2 unhybridized 2p orbitals. So it's going to put 2 electrons in each of those sp and 2 electrons in the 2p. Okay, so let's try and draw this. So we have our carbons, and they each will have 2 sp hybrid orbitals. So we know one is going to go to make the sigma bond here. So that's our sp. And here's our other sp that's going to go make the sigma bonds with hydrogen. So there's our sp orbitals. Okay. Now we need to draw our 2p hybrid orbitals. Okay, so if we look, each carbon is going to have 2 2p's. So I'm going to draw, here's one of my p orbitals for this carbon, and so that's above and below the plane, and then we need the other ones coming like into and out of the plane. So the way that I draw this is I kind of draw it on like a slant, and then I'll make them look different. So like if I do this one as dashes, maybe this one has, I don't know, dots, so they look different. However you want to do that, just make sure they look different. And again, this carbon will have one above and below the plane, and going into and out of the plane. So again, I'll make one with dashes, and the other one with, I don't know, dots, where you can make different dashes or whatever makes you happy. Okay, so we've got our sigma bond going on here, and we know that in a triple bond, we have a sigma bond and 2 different pi bonds. So the sigma bond we're showing is the direct overlap between the atoms. 1 pi bond will happen above and below the plane, so that will be one of them. And then the other one will happen coming, behind and in front of the plane. That will be the other pi bond. Okay, so we've got the sigma bond between the 2 carbon atoms. That's from the hybrid orbital. And then we have the pi bonds coming from the unhybridized 2p orbitals. And then, of course, we have sigma bonds going to each of these hydrogens because those are single bonds. Let's try one that's a little more complex. Look at this mess. So we've got a lot of different things going on here, right? What I would do first is go through and kind of plan out what everything, the hybridization of all of the atoms, and where you have sigma bonds, where you have pi bonds. So let's go through that. So if we look at this nitrogen here has 4 areas of electron density. It has 3 single bonds and the lone pair. So if it has 4 areas of electron density, this nitrogen is sp3 hybridized. It's forming a single bond with the carbon. So that's going to be a sigma bond. And these are all sigma bonds as well. This left carbon here has 2 areas of electron density, the single bond to the nitrogen and the triple bond to the other carbon. So this carbon is sp hybridized, as well as this other one. Just while we're looking at it, that one also has 2 areas of electron density, so it will also be sp. In this triple bond here, this will be a sigma bond and 2 pi bonds. So that's going to be fun to draw. We've got a single bond here, so this is a sigma bond, and this is a sigma bond as well. And then the oxygen has 4 areas of electron density, so that is going to be sp3 hybridized. So again, this looks like it's going to be real fun to draw. Let's try it out. So here we go. I'll fill this in up here. So this was sp3. We've got sigmas. We've got these 2 guys as sp, and we've got a sigma and 2 pi's, sigma, sigma, and sp3. All right, here we go. So I'm just gonna kind of go left to right when I'm working on this. So let's start off with the nitrogen. So the nitrogen has 4 sp3 hybrid orbitals. So we go 1, 2, 3, 4. 2 of them are going to make sigma bonds to a hydrogen. 1 of them is going to have a lone pair, and the other one is going to make a sigma bond to the next carbon. So that carbon that's here will have 2, right, sp hybrid orbitals. So if we think about these sp carbons, the sp carbons are going to have 2, sp hybrid orbitals and 2 unhybridized 2p orbitals. Okay, so we've got this 1, 2, those are going to be our sp orbitals, and we can show the electrons in that sigma bond with the nitrogen. Okay, and then it's going to have 2 unhybridized 2p, so it's going to go above and below, and then into and out of the plane. So again, I'll make maybe this one with dashes and this one with dots, or whatever makes you happy. All right, so that's going to be that carbon. To finish this off, we really need the other carbon that's also going to have 2 hybridized sp orbitals. You can show the electrons in that sigma bond there. And then it's going to have 2 2p orbitals unhybridized. So 1 above and below the plane, 1 going into and out of the plane. So again, make one with dashes, one with dots, whatever other designs you feel like doing. All right, so we've shown the sigma bond. Here's one of the pi bond that's going above and below the plane, so that's 1 pi bond. and the other one is going into and out of the plane. So that's our second pi bond. Now we've got our carbons taken care of. We can move on to our oxygen. Our oxygen is sp3, so it has 4 hybridized sp3 orbitals. So we go 1, 2, 3, 4. Those are all sp3, and we'll show our electrons here in that sigma bond. Realistically, I know it has it shown with the lone pairs separate or separated, right? We've talked about the fact that oxygen should have its lone pairs next to each other. So I'm going to redraw this with the lone pairs next to each other to be more correct. And then we'll carry down, or we've got that last one making a sigma bond with that hydrogen there. So there you go. That is the flower diagram of that molecule. So we've shown all of our, and it's a good practice to go through and kind of label things just because it gets a little messy, right? So we've got our sigma bonds, we've got our, our 2 pi bonds shown. So that's a pretty good molecule. So just one last topic. This is our last slide. So we can have these structures, and I know, so all of these junctions, I know we're not super familiar with this, but these are all carbons that look like this, and this is benzene. And so benzene can have 2 different resonance structures. We can draw all of the benzenes, we can go, double, single, double, single, double, right? Or we can go single, double, single, double, single, double, right? And those are going to be kind of interchangeable. It's not necessarily the one on the left. It's not necessarily the one on the right. It's somewhere in between. And if we think about what we know about double bonds, right? Double bonds are these pi bonds, and they exist above and below the plane. And so if we think about it, right, these electrons in this last picture with the green donut-looking things, because the pi bonds exist above and below the plane, the electrons can kind of go in this, circle. Same thing in the bottom circle. And so this is what we talk about. We talk about delocalized electrons in bonding can help explain this resonance. Because these pi bonds exist above and below the plane, they can kind of interchangeably go from one structure to the other. Which is really cool if you think about it. But again, you have to have these pi bonds in order to be able to have resonance, because the electrons need to be above and below the plane. If all we had were sigma bonds, then the electrons would exist directly between the atoms in those bonds, and we wouldn't have the ability to kind of move them around our structure. But again, since we have pi bonds that exist above and below the plane, they can move around. And that is the end of today's lecture. It's pretty short. It's just on getting this practice drawing flower diagrams. So you're going to need to go get some experience drawing these. They're not so bad, but they can be a little bit weird to start drawing at first. So as always, send me any questions if you have them, and we'll continue Chapter 10 next time.